Welcome! This time I'm trying out a new format. My previous videos have been very specific to game development using Go.Engine, but in this video I want to talk about the broader topic of random numbers and how to use them in your game project or really in software projects in general. I'll give tips and tricks of how to set up random number generation, how to create them efficiently, and how to use them for random shuffle or for non-uniform distributions. But first, let's set the stage and talk a bit about the concept of random numbers. At the high level, we want to generate unpredictability. In a game, this could mean random actions by computer opponents or random loot for player to discover. Or in a physics simulation, this could mean adding thermal noise to a system of particles or deciding on Monte Carlo simulation step. A standard way to bring about uncertainty while executing computer code is through random number generation. There's two broad categories of generators. First, there are the true random number generators. These use external physics processes that are understood to be random to generate sequences of numbers. For example, device noise is a common source of randomness. Other possible sources include, say, rolling dice to get uniformly distributed random numbers, or measuring radioactive decay intervals to get Poisson distributed random numbers. If they are correctly implemented, these generators are very good at generating unpredictability. The downside is that they are very slow. Also, it can be hard to reason about validate the statistical properties of the random sequence, because to do that we need a correct model of the underlying physical process. Therefore, instead of going for true randomness, it's common to use pseudo-random number generators. These are algorithms that are designed to generate uncorrelated sequences of numbers that follow a specific distribution. The way they typically work is that they take a seed number that's used to initialize the internal state of the generator. The seed could be a true random number. And then the generator churns out new numbers when called while updating the internal state between each number according to the rules of the algorithm. The nice thing is that these generators are fast. They are also reproducible, which means if it's easy to analyze the properties and run a set of statistical tests to validate the quality of the output sequence before putting the generator into production. The upshot is that because they are using deterministic algorithm, the sequences themselves are fully deterministic. So they aren't really generating randomness in abstract sense. Since they are generating sequences that are unpredictable, it's hard to guess the next number by just looking at the previous numbers. There's two subclasses of pseudo-random number generators. Cryptographically secure pseudo-number random generators and what I've called fast generators for the lack of better name. The cryptographically secure ones are designed in a way that it's hard to reverse engineer the internal state and predict the next number given the earlier output sequence. This property makes them useful for generating things like encryption keys or tokens. The fast generators are designed for cases where you don't worry so much about the state getting exposed, but you need random numbers in bulk quantities. An example could be a Monte Carlo simulation where you might need tens of millions of random numbers and generating them becomes a significant cost in the performance budget. An example of such generator is a Mersenne twister, invented by Professor Makoto Matsumoto. The generator has a repeating period of 2 to the power of 19,937 minus 1. It's a very large number. For comparison, the estimated age of the universe in nanoseconds is about 2 to the power of 88. Note that the repeating here applies to the sequence as a whole, not to the individual values which can appear much sooner. This is the subclass of generators what I'll be focusing on for the rest of the video. Also, from now on this video, when I say random, I really mean pseudorandom. Let's look into some examples. I'll be using Python and NumPy library for these examples. First, let's look at initializing the random number generator. It's good practice to always set the seed. I like to have what I call debug and production modes. In debug mode, you use some fixed seed value to get a repeatable sequence, which makes it easier to reproduce potential issues. In production mode, you try to randomize the seed itself to get a new sequence every time. Say if you want to give a player of your game a new unpredictable session. A simple trick is to use the system time in milliseconds or nanoseconds. It's random enough for most practical purposes. So let's try this out. So we see the result for the debug mode and production mode. But if we run this again, we can see that the debug mode gave the same result, whereas the production mode gave a new sequence. If you want to be really meticulous, you should first warm up the generator to let its internal state to reach equilibrium before starting to use the numbers. To do this, we generated some large number of random numbers and threw them away. So what's the fastest way to generate random numbers? First, let's try generating 1,000,000 of them one by one using NumPy's random integers function in a loop. We saw it took about a second. Then let's generate them in a batch using the vectorized form that returns on an array. We can see that the batch generation is much faster. So if you know you are going to need lots of random numbers, it's best to create them in a batch ahead of time. Next, let's talk about a bit more advanced use cases that go beyond uniform random number generation. Say we want to shuffle a deck of cards, but in a way that ensures that the cards are really well shuffled, without statistical anomalies like subsequences of unshuffled cards or bias towards certain ordering. A straightforward way is to use two lists. One with 52 unshuffled cards and another empty one. Then pick a card from a random position on the first list, pop it out, append it to the end of the empty list, and repeat until the first list is empty and the second list has the cards in random order. Let's check this out. So we got a pretty reasonable hand. However, there's a nice trick that we can use to make the shuffle a bit faster and the code a bit simpler. The random array sorting method. First, create an array of unshuffled cards, then create an array of 52 random numbers. Then sort the card array by the random number array. This works because the ordering of numbers in the random number array is also random. In NumPy, there's a function called argsort that can give us the corresponding indices. So let's just try this out too. And we got our result. Looks good. It's transposed because it's a NumPy array. The sorting method is theoretically faster as it's scaled as O n log n, with sorting being the bottleneck, while the first method that's list-peak based scales as O n squared. That said, realistically for a deck shuffle of 52 cards, it doesn't really make that much difference, but if you're shuffling tens of millions of numbers, then the speed up might be useful. Let's talk about another scenario that goes beyond uniform random number generation too. Let's say you want to model an event with outcomes ranging from common to rare and extreme. Say damage caused by a monster attack, or another example could be Gaussian random walk type movement. To do this, you need a non-uniform distribution. A normal distribution is a common choice. The frequent occurrences are concentrated near the center of the distribution, and the rare occurrences are in the tails. So how do we draw numbers from this distribution? A general, theoretically sound approach is to find the cumulative inverse distribution function and feed it uniformly distributed random numbers which would transform them into the target distribution. However, in practice, it turns out that the inverse CDFs are often numerically expensive to evaluate, and this has led to development of numerical algorithms, such as the class of rejection sampling methods, which come in many variants, such as the basic method or the ziggurat method. But we don't need to go into the depths of these algorithms because for the normal distribution, we are in luck. There's a trick called Box-Muller transform that lets us trade two uniform distributed random numbers into two normal distributed random numbers using a pair of simple formulas. The formulas are straightforward to derive, but a bit tedious for this video. The key observation is that you're sampling 2D normal distribution on a plane, which separates nicely into two 1D normal distributions. Also, these formulas can be vectorized, so you can create a large number of pairs of uniform random numbers and quickly transform them into normal distributed. So let's try this out. Here are our 5 plus 5 normal distributed random numbers. One thing you have to be careful with is the evaluation of the natural log, as it goes to negative infinity as x approaches 0. So you should make sure that your uniform random number generator won't return exact 0, and you might want to truncate values close to 0 to stay away from numerical instabilities. One final note is that numerical libraries often have built-in functions for common use cases like shuffle or normal random number generation that can make things easier. Just make sure that you have a quality implementation. Thanks for watching. Subscribe to the channel to get updates on new videos.